Okay, thank you, Stefan.
Thank you.
Now we're coming to the last talk before the coffee break. The talk will be given by Dr. Ahmed BENTAIB. He obtained his PhD in 1993 in applied mathematics in Lyon, France. He has more than 20 years experience in hydrogen risk issues and safety licensing. And currently he is an expert in nuclear safety at IRSN, in charge of R&D and safety assessment. He coordinates the mitigation project, which is funded by the French agency and the Samconet under Nugenia umbrella. So you will.
Okay. Thank you, Mr. Chairman, for this kind introduction. Good morning, ladies and gentlemen. My talk is about severe accidents. It's somehow different from the previous talk. And when we talk about severe accidents, it means that we are in condition to have a core melt and the possibility of a reactor vessel rupture, and also the possibility to have combustible gas release inside the containment with the possibility to have hydrogen and carbon monoxide explosion. This is basically what happened in Fukushima Daiichi. And also the fission product release inside the containment, reactor containment, and outside. This is, I will do my best to present you the main outcome of 6 projects dealing with this different topic addressing severe accidents, means core behavior inside the inside the reactor vessel, and also what happened inside the containment, and how we can reduce the source term release outside the containment. My co-authors are the coordinators of this project. I have to mention here that I was not involved in any of them. This is, please be kind with your questions. I will do my best to answer your questions. So, as motivation, this Fukushima Daiichi accident, after this accident, the stress test performed in Europe and outside Europe underlined the need of further investigation to improve the severe accident management strategies, including external hazard. And many of the recommendations of this stress test was to upgrade the existing nuclear power plants by implementing new devices as recombiners or containment filter venting systems. And to achieve these goals, basically there are 2 ways to do it. The first one is to fill the gap of knowledge and to reduce the uncertainty related to this phenomena participating in severe accident. This is basically what was addressed in the framework of ALESA, SAFEST, and IVMR projects. The second way to achieve these goals is to develop new mitigation systems and strategy to reduce the source terms. Source terms means what could be the fission product released outside the containment, and to ensure the heat removal, basically where we are in condition of station blackout, when we lose the ultimate heat sinks, how we can develop system to ensure somehow this heat removal. This is basically what was addressed in the framework of PASAN project and also as CO2 HERO project. Of course, all this knowledge coming from experimental data performed in this project had been hosted in, we had to capitalize somehow this knowledge in tools, in safety tools. And this was the objective of CESAM project, is to improve the modeling of severe accidents and the severe accident management of ASTIC code. ASTIC code is really the European code for severe accidents, and to make it, to improve the ability of this code to address also different design including PWR, BWR, IVMR, and CAN-do technologies. So I will give you an overview of each of the 6 projects, and I will not go in details, it's only the main outcome of each of them. I will start by what happened during in the reactor vessel, and the first project is safest project, the acronym of Severe Accident Facility for European Safety Targets. The objective of this project, is coordinated by KIT and the consortium. You have many partners from Europe, but not only. You have also the connection with the Japanese colleague, with this CLAD laboratories created after Fukushima to deal with Fukushima Daiichi decommissioning. And the objective of this safest project is to create an integrated pan-European laboratory for severe accident research. The idea is to have a common vision on what are the most important issues regarding corium research and to deal with. And of course, within, to develop a research roadmap on this issue and to establish access to safest research infrastructure to perform experiments dealing with core degradation in vessel and ex-vessel melt situation. And also, in front of this project, is also to increase the ability or the knowledge of and the instrumentation and quality of R&D of these experimental infrastructures. The main outcome of this, of course, I forgot this. The safest project allow, as I mentioned before, the development of roadmap. This based on the roadmap, 2 calls for proposal were launched in 2015 and 2016. Altogether, within these 2 calls, 16 experiments or experimental series had been performed dealing with different aspects of corium behavior, characterizing the corium properties, fuel coolant interaction, and MCCI. Different topics were addressed in frame of this performed experiment. Of course, this performed experiment are useful to improve the modeling of implemented in safety tools. The second project is ALISA, is basically adopted the same approach. The only difference is at the connection between Europe and China. There are 2. This project is was also coordinated by KIT in Germany, and 2 partners from Europe, KIT from Germany and COA from France, was involved, and 6 partners from China, including academic research institute and also industrial. And the idea is to allow the access to large infrastructure dealing with not only corium behavior but also hydrogen dispersion and combustion within large facilities. In framework of this ALISA project, 2 calls for proposal were launched and experimental were performed dealing with core degradation and vessel melt behavior and retention, fuel coolant interaction, containment and hydrogen behavior, including dispersion and combustion, passive system, and also corium properties. The results are very valuable for code and model development, And based on this, the results coming from these two projects and from the previous new project, IVMR, dealing with investment retention strategy for higher power reactor was launched in 2015 with the participation of more than 23 partners coming from Europe and from Asia. And the main objective of this project is really to see how we can avoid the reactor vessel ruptures. The idea is to ensure to cool the external surface of the reactor vessel, and of course to extract all the heat fluxes produced by the corium, is to ensure that the critical heat fluxes outside what we can extract from this surface is higher than what could be produced during by the core melt. And the methodology initially adopted for low power reactor is really to ensure that we can extract higher heat fluxes, and to do that, the approach is based to make a balance between the produced heat flux here and what could be extracted at steady state. And in the framework of this IVMR project, it seems that during the transient, the heat flux may be higher than the heat flux what we could have during steady state. And during the framework of this project, the methodology had been revised to take into account these transient conditions, and based not only on the balance between the heat flux inside and outside reactor vessel, but on the criteria based on the residual thickness of ablated vessel, and which is supposed to use safety code and the mechanical code to do that. Of course, this project is still ongoing, and still issues regarding this stratified condition what we can have during this transient, which are responsible of high heat fluxes. And the work is ongoing to deal with this issue. Now I will move to what happened in the containment and dealing with the PASAM project. PASAM, the objective is to improve system to limit radioactive release outside the reactor containment. This project was coordinated by IRSN with the participation of 9 partners, including research center and also industrial, you can see here. And the main objective was double. The first thing is to explore what could be the way to enhance the existing mitigation system. I mean, for the moment, all the containment filtering system is based on either pool scrubbing system or sand bed filters. And the idea is to see how we can improve this mitigation system. For example, for the pool scrubbing system is to maintain the outcome of this project, to maintain a higher pH, to avoid any late iodine release. And for the sand bed filters, as we have in France, the possibility to add metallic pre-filter to enhance the efficiency of filtration. On the other hand, it was also the opportunity to investigate the ability of innovative system to achieve large system attenuation by using experimenting new devices dealing with acoustic agglomerator, which means that that small particle will be we try to make it more bigger are the particles is the filtration is, and also experimenting also zeolite component to deal with iodine reduction release. If we look to this main outcome of this PASAM project, this project allow the production of a large database for existing and innovative mitigation system regarding gases iodine retention, either molecular or organic iodine, regarding hydrodynamics for scrubbers, and also long-term stability of trapped component. This project also allow a deeper understanding of the phenomena underlying their performance. They allow also development of sample model and correlation, which were implemented in Aztec code, and also have an estimation what could be the order of magnitude of the system reduction for each filtration system. So this is for PASAM project, and all the knowledge gained from this safest ELISA, IVMR, and PASAM, the lesson learned was used to improve the model, European Aztec, European code for severe accident Aztec code, developed by RSN. This project was coordinated by GRS in Germany, and allowed the improvement of and the validation of the Aztec code, and to also improve the ability of Aztec code to be connected to a dispersion, atmospheric dispersion tool to be used for emergency configuration, and also to investigate to evaluate the severe accident management guidelines. Within the work performed in framework of this CESAM project allowed the validation of most physical phenomena with this new version of Aztec to produce a generic nuclear power plant input deck for this for Aztec community with different reactor design. The last project is dealing with heat removal, and the objective is developed a proof of concept which of this device, which could be plugged on the. Sorry, I forgot to mention that this project was coordinated by Duisburg Essen in Germany, University in Germany. The idea is to develop a device which could be plugged in the circuit and allow the heat removal. This device is based on Brighton cycle, using this supercritical CO2 as a working fluid, and allow this working within the extracted heat will be used also to produce electricity more than needed, and this additional electricity could be used to recharge batteries needed in case of station blackout in nuclear power plants. Within this this project, a prototype was developed and designed, and the evaluation of a stick head was performed. The quality assurance has been demonstrated within this loop, and this safety code was used to evaluate this, the benefit of this device. And of course, as I mentioned before, the proof of concept has been performed during this project, and now the follow-up of this project, calling now is CO2 NPP, which is coordinated by EDF in France, has the objective to upgrade this technical readiness level from 3 to 5, which means that we are dealing with pre-industrial devices. So let me summarize my presentation. The main achievement of this project is allowed a better understanding of the severe accident phenomena, such as core degradation, core melt, and hydrogen deflagration, and contribute significantly to reduce the relevant the related uncertainties. In framework of this project, we have development of novel mitigation equipment for heat removal, the improvement of innovative strategy in support for the in-vessel retention and the source term reduction, the improve of the ability of the ASTIC code, and in framework of this project, also effort had been made for knowledge dissemination and education. Many PhD were involved in this project, and the demonstration prototype of this removal heat device was installed in a PWR glass model in Essen in Germany for teaching. Production of a large number of numerous peer-reviewed publication, organization of several workshops, and also participating to AEA and OECD projects within this state-of-the-art report or contribution to IEA CRP. So I would like to take the opportunity to thank the financial support on behalf of my co-authors, the financial support of Europe. Thank you for your attention.
Thank you much for the presentation. There are so many projects, it's hard to get an overview on all the projects, but are there any questions? Oh, there are many questions. Let's start with you.
Frank Carré. Thank you for your very comprehensive presentation. You mentioned the fact, well, the significance of supplementing the existing database and also the working towards reducing uncertainties in understanding basic phenomena. In addition to, I think, reducing uncertainty in combining, let's say, phenomena that have been investigated on separate effect experiments. Do you think that let's say the progress of numerical simulation or let's say artificial intelligence might help, let's say, better focus future, let's say, experiments, and maybe, let's say, to identify some time where more analytical type of experiments will be needed than really corium experiments with large amounts of corium?
For sure, the uncertainty, the effort has been made to reduce the uncertainty, still windows to improve, to reduce again this uncertainty. And there is a new project called MUSA and coordinated by CIMAT in Spain. We're dealing with this topic. The idea is how we can reduce the uncertainty when we couple this complex phenomena dealing with severe accident. Of course, they still need, if I understand well your question is how we can use artificial intelligence to design new
analytical experiments than, let's say, integral experiments with large amounts of corium.
Yeah, which, if I understand well, it's before doing this, we have to have maybe a complete picture on the behaviors of the coupling between these phenomena. And I guess that we are not able now to do it, to replace virtual intelligence by new experimental data.
Okay, there's one more question.
Another question concerning a severe accident, IVMR project. You indicated that you tried to reduce the degree of conservatism. How well did you succeed? In the methodology of corium formation and the rupture of the reactor vessel through concentrated heat flux.
Yeah. This project, IVMR project, is still ongoing. And what I mentioned here, that the methodology has been revised to use as criteria not only the heat flux balance between inside and outside the reactor vessel, but based on the residual thickness. And the main challenges now is regarding when we have this inversion of corium metal layers, and this which drive a high fluxes, which is really challenging, and they still work on it. And what I heard from the coordinator, that they are working with the new experimental data to learn more, develop more, and enhance these models.
Okay. Is there any urgent question? I hope it's a short one. It will be the last one.
Well, it is a short one, and it's kind of a specific one, so I understand if you do not know the answer offhand. It's related to computational aids that are used for severe accident management. So what are the criteria that are used in Europe for core quench calculations?
I have to say that I don't have the answers.
That's fair. And the other question is related to, to Aztec code. So is it also the alarm parameter code? And how many nodes would you, no, it's not, somebody is shaking their head.
Aztec is lamp parameter code.
It is a lamp parameter. And how many nodes do you have for simulation of the core?
I'm more familiar with the containment. For the containment, we use basically from 20 to 80 nodes. And for the core, I have to check. Sorry.